Welcome to the last talk of this day. It was a very interesting day, but the last talk is promising too, because we have the great pleasure and the honor to have with us Johannes Royset, that is a professor of research in California, more precisely at the Naval Postgraduate School. He has done many contributions to stochastic optimization, to optimization in a large sense, to Monte Carlo sampling in optimization. So really, it's really great to see you today, and the floor is yours.
Thank you very much. Thank you for this great workshop. Really enjoying it. Today I'm going to talk about an approach to optimization under uncertainty. That is what we call diametrical stochastic optimization. This is an idea that is rather simple, I think, but is an idea that hasn't really been studied, and we'll see today maybe that it could be a promise in this particular direction. So let's think a little bit about optimization under uncertainty more generally. Of course, what we've been talking about the whole week is to minimize some sort of expectation. There's really good reason for doing that. It goes back to Van Neumann and Morgenstern. Of course, much of statistical M estimation is involving such minimization of expectations. So these are fundamental problems that we would like to solve. Of course, there are many challenges associated with such problems, and many have been listed throughout the week. Just very briefly, of course, is that we often have to pass to some sort of sample average approximation. Some people call that a data-driven approach. In statistics, machine learning, one will refer to empirical risk minimization. But it's nothing but, you know, you might have some sample xj of your random vector, and optimization, which takes place over W in my notation, or some sort of loss function psi. Okay, so this is fine, and the question, of course, which has been with us for a long time, is how can we make sure that this sample average approximation is representative, that it produces solutions that are relatively close to those of the actual problem. And this is a fundamental question. There will be many strategies to try to kind of get as much as possible out of the data that you have available. And one possibility, of course, is through regularization, which is common in statistics, where the sample average has been augmented with a regularization term. And this might really help to obtain better solutions in some sense or another. One possibility, of course, that has been a bit fashionable last decade or so is the business of distributional robust, where we introduce a maximization over a family of probability measures. So now the expectation that we're looking at is not only one expectation, but many expectations, and we look at the worst case. And there can be a really good reason for doing that, and this can certainly be a way to accommodate the fact that we're dealing with data, we're dealing with incorrect or at least inaccurate probability measures. And by introducing this supremum, we are a bit more conservative. Very closely related to this is the business of risk-averse optimization, where one will introduce a measure of risk. Of course, we know, for instance, if such a measure of risk is monotone, regular, positively homogeneous, we can get back to the distributional robust, where certain families of measures will come out of that. And so all the motivation that we have for distributional robust is often typically the case there in the risk-averse setting as well. Okay. In learning, it's been common as of lately is to look at so-called adversarial training. And what is that? Well, now we are somehow trying to do better by introducing a maximization where the parameter vector v is inside some sort of ball maybe, and that has been added to the data. So we're introducing some sort of noise in a worst case sense, and this could be reasonable for many reasons, in particular to absorb the fact that the data that we have observed might not be entirely a representation of the population. And there could be also other reasons. For instance, we might have an adversary, and that adversary is going to mess with our data in a deliberate fashion, and maybe we can account for such things by formulating such a model that in one way or another is somehow trying to improve on the sample average approximation that we had earlier. What this talk is about is just another way of trying to improve upon the sample average approximation that we have on top. I call it diametrical stochastic optimization. Sometimes when we talk to machine learning people, I talk about diametrical risk minimization, just analogously to empirical risk minimization. That is the typical name for the sample average problem in that learning and statistics community. So actually, throughout this talk, I'm going to adopt a bit of a machine learning type of language, and I'm going to talk about the diametrical risk minimization. The diametrical stochastic optimization is the same thing. Okay. So before we get into the detail about what is this diametrical risk minimization, let's think a little bit fundamentally about what is the trouble that we have with this sample average that we have up there. Why are we going through all these exercises to try to find a better model in some way? So what are the challenges that we are facing? Well, I talked about we have the actual problem, and then we have our sample average. What is the problem with the sample average? Of course, it brings in an error. We would like to discuss how big is that error. So imagine the following situation, that we go ahead and minimize the sample average. And through that process, we obtain a W, I call it Wn, because we're using sample size n. Okay. So one thing we wonder about is that Wn, if I plug it in to the population problem, where the true expectation is, I wonder how far off will I be? So in particular, how far is the population expectation at this particular W compared to the sample average value? And this will be one way to think about an error. Notice that I'm looking at this from a one-sided point of view. I'm not taking an absolute value or anything like that on the left-hand side. I look at it on a one-sided way. And there's probably a good reason for that, because we know that sample average approximation will have a downward bias. So on average, the minimum value up here will be on the low side. So on average, this quantity here will be smaller than the minimum value of the actual problem. Okay. So I think it makes sense to look at the error in this particular direction, and let's focus on that throughout the talk. Okay. Okay, so if we have that, let's look at this cartoon, which is trying to schematically illustrate what are the main challenges. So the black dashed line gives the expectation function. So that's the population problem, the objective function that we have in the actual problem. And then I've compared that with the sample average. That is a solid red line. And think about that is the objective function in the sample average problem. Okay, And of course, if the sample size is pretty large, one will hope those two are pretty close, and I guess they are most of the time in my picture. However, there's always a possibility, and this is of course something that we are worried about, that the sample average might have a dip that we see over here that is somewhat spurious in the sense that the expectation function does not have that dip. So if we apply a minimization algorithm to this sample average, we might end up in the valley to the right. This will be bad news, of course, because if I evaluate that W that I obtain, I guess this is my W here. If I evaluate that relative to the actual objective function, the population problem, that's up here. So now I have an error that is that whole height here. So that would be an example of a big error of the kind that we're talking about here. So this will be an unfortunate situation. Of course, the situation would have been much better if, when I minimize the sample average problem, I landed over here in the valley to the left. Because there, if I plug into the population problem, the error is much smaller. And that would be good news. So I guess in one of those cases, there's a big downward bias in the right valley, and there's a smaller one in the left valley. So what are the circumstances that will produce such sharp valleys that we have on the right? And what are the circumstances that will avoid that? So we're looking at a landscape that is more involving valleys of the kind that we see on the left. And these are the things that we're going to try to think a little bit about through some simple examples. Here's my first simple example. And it's actually just involving a random variable that is Bernoulli. 0, 1, probability 0.5, 0.5. And the objective function that I want to minimize is my psi, as we're talking about the whole time. And what is my psi? Well, the psi has not two outcomes, right? Either x can be 0 or x can be 1. If x equal to 0, then we have the solid blue line. That is the function. This is given. If the random variable is 1, then we have the dashed blue line. So that's also given. Okay. So on average, what are we looking at? We are looking at a function that is exactly a flat line, the 0 function, right? So the actual problem, the population problem, is to minimize the 0 function, which of course everything is equally good. The minimum value is 0, and we know everything about that. But now let's see what happens if we sample. Okay. So if we sample with the probability roughly 0.5, we are going to find, get more ones in our data than zeros. So when we take the sample average of these blue curves, being it the solid or the dashed, if I have more ones, the sample average will have a dip at the origin. So indeed, the minimum of the sample average will be 0. Because there will be more downward spikes than upward spikes. And we can look at how big error are we going to make in the sense that we talked about by comparing now that 0 that we found, plug it into the population problem, and compare what the sample average says. And it's easy to compute that the error is something like this, where there's a row, and then there is some kappa, and there's something divided by n is the sample size. So we know that error goes to 0. So I guess that's good news when n goes to infinity. But there's a parameter here, kappa, and what is that? Kappa, as you see from the picture here, has to do with Lipschitz continuity of this objective function. If kappa is large, that means that it's rather spiky there. So if kappa is large, we get a larger error down here. So the point I'm trying to make is the Lipschitz continuity of the loss function that you're considering is going to influence the error that you're going to have when you're solving your sample average problem. Let's look at another example. Again, I'm going to stick to an x that is Bernoulli, but now I'm going to change up a little bit the loss function that I'm minimizing. Now, psi, if I get an outcome of 0, is going to look like this, 1 over w, when w is positive, and then otherwise it is 0. If I get an outcome of x equal to 1, then the loss is negative 1 over w. So I guess it's that downward curve that we see here. And again, for w less than 0 is going to be the same. Again, if you take the average now, of course, the average or over the population is just going to be the 0 function. And again, we know what the minimum of that, the minimum value is 0, every w is equally good, and all those things. But what if we do a sample average now? Again, with roughly probability 0.5, we get more 1s than 0s. That means that we're going to have more downturns. And if I have a downturn, if I minimize such a thing, of course, things will go through the floor and I will go down to minus infinity. The sample average problem will be unbounded in that case. And if you look at the error in that case, the error in fact tends to infinity. So this was particularly bad, that the empirical risk minimization is just good old sample average approximation is way too optimistic, and in fact the error can be arbitrarily large, as this example shows. Of course, there's a long, lot of literature on this subject, and let's talk a little bit, very briefly, about the role of Lipschitz modulus in this setting. I alluded to it earlier that the Lipschitz modulus will have to play a role, or typically will play a role, when it comes to quantifying the error of solutions obtained by sample average approximations. So the Lipschitz modulus shows up in many of these classical results in one way or another. From a more maybe practical or empirical point of view, in the statistical learning literature, there's often a discussion about what is really the landscape that we are moving around in. And with that, I mean, if we look at the objective function in the sample average problem, and think about that as a landscape in W, in the optimization variables, there are ups and downs, and hopefully there's a bottom where the minimum is. How crazy is that landscape? How chaotic is it? And there'd be different studies trying to look at that from an empirical point of view. And this goes back a little bit to the picture that I showed you in the beginning. Are there sharp valleys in that landscape? And that can potentially be somewhat of an indication of trouble when we're dealing with sample averages. Of course, in the stochastic programming literature, there's also much work about errors associated with sample averages. I'm not going to go into the details of that, but all of this is highlighting that what is driving the error? Well, it is the Lipschitz modulus typically, and other type of regularity properties. So now, what is this idea that we are proposing to try to address these challenges that we have associated with sample average approximations. And the idea about diametrical risk minimization, or equivalently diametrical stochastic optimization, is to do the following. To introduce a min-max type formulation, but now the maximization is going to be done a little bit differently than what we talked about earlier. The maximization is going to involve a variable or a vector v, which is added to the decision variable w. So let's contrast this, for instance, with adversarial training, which is so popular in the machine learning community. That has a similar flavor to this, except that the v is added to x. So what is perturbed is the data. What we're doing here is something different. Here we're perturbing the decision. Also, let's make a comparison with distributionally robust optimization. Of course, in distributionally robust optimization, we are in the probability space, space of probability measures. So what is going to be perturbed or taken a maximum over are the probability distributions. So again, you're working on the data side. You're making a change to the data in some sense. We're doing something different here. We are working on the W side, and we're making a change to the decision. So what we want to see is that if you go ahead and solve this min-max problem and obtain a W, that W has a tendency to actually have a low true objective function value. On the population problem, that W will look good. That means that you have identified a W that is more in this region than in this region. So somehow, by solving this alternative problem, you're promoting solutions of the kind of the left valley more than the right valley. And we're going to try to formalize that as we go along. Some historical remarks. This thing that we call diametrical risk minimization has a bit of a history. In fact, it goes back more than 100 years in some sense, at least if we're generous. We have the concept of modifiers. And what is a modifier? That is really a way of changing an optimization problem by kind of smudging out the value of the objective function by changing W a little bit. Typically, that's done with some sort of with a kernel or like an averaging process. We're doing, of course, something a little bit different here. We're taking a supremum, but maybe in spirit, what we are doing can be related to modifiers. Also, of course, the diametrical risk minimization problem is nothing but a robust optimization problem, a more specific one. So it has all the history that goes with robust optimization. But here is a very prominent line of work due to Adrian Lewis, which I think was the first one to maybe address this systematically from a certain angle, at least. So in a technical report from Cornell in 2002, Adrian Lewis looked at this type of min-max problem, but in a setting, not in stochastic programming setting, but basically in a setting where we just have some objective function, forget about the data. We just have some objective function psi, so forget about this sum. And we just want to minimize psi with respect to W. And he introduced this V robustification. He called it a regularization technique. And he discussed how this could be beneficial, for instance, promoting things like Lipschitz properties and other things from an otherwise rather irregular psi. And he even discussed how in certain cases, particularly quadratic psi, one can even, this min-max problem can solve it using semi-definite programming. There have been some similar ideas in more applied settings, more specific problems, without getting into the details. It's an interesting work, but maybe a bit more specific. But let me highlight one thing. That was this very interesting paper coming from Rob Freund and company at MIT, where a paper in operational research in 2013, they talk about fabrication adaptive optimization. Their motivation was not a statistical problem. There was not stochastic optimization, not statistical learning. The motivation was simply the fact, which is an important practical situation, that when you optimize something, find an optimal W, and you give it to some engineer for implementation. The process of implementation might introduce various errors. Maybe it's not possible to implement the plan precisely, and to account for this type of inaccuracies, they introduce what they call this fabrication adaptive optimization, which is essentially the problem or the kind we're talking about above, where we are minimizing sub W, we take a supremum over V, but there's no sum and things like that, there's no data, just some psi, and one try to make that W somewhat more robust to changes. And they could reason that for the sake of implementation. There's also been in the machine learning community, after we put up our paper in the archives, a couple of other papers came about. The first one is from Yisun Wang's group in Peking University, which follow similar ideas with less analysis and things like that. But let me not spend too much time on that. But let me just make a small motivational remark why it could make sense to add such a V in a machine learning setting that is completely distinct from our original motivation. Our original motivation was to try to improve on sample average approximation to get smaller errors due to sampling, getting bounds on errors under circumstances when they otherwise would be difficult. But there is another motivation, and that has to do with implementation of large, say for instance, classifiers on devices with poor, limited battery capacity, limited memory capacity. In such situation, imagine that you're in a typical machine learning setting where the W that we're talking about is rather large, say 12 million dimension or something like that. So if you have 12 million dimensions and you need to access those 12 million dimensions and those 12 million numbers are in double precision, you choose up quite a bit of memory, and to access those things will take energy, and there are things you might be worried about. So what is sometimes done when you want to put a classifier on a device is to pass to lower precision, maybe from double precision to single precision, or do some other approximation of W. And just purely from an implementation point of view. So of course, in such a situation, if you worked hard on finding an optimal W, some of that is a bit lost now, right? When you implement it in an approximate fashion. So it could make sense from that point of view to robustify by introducing a V. So you get a solution W that is good, not only at face value, but also good if you change it up a little bit by adding a V. And that can account for the fact that in implementation, it's actually not a W that's implemented, but it's a W with some changes. and you want that to be good. Of course, this is exactly the same motivation that Rob Freund had in a different setting, and that is remains in some sense relevant here. So there could be several reasons for why you want to solve such a diametrical risk minimization. Okay, let's go back to our simple examples. And you remember this one, this was my first example. The question is, how does diametrical risk minimization do in this setting? Remember, plain old sample average approximation gave us an error of 1/n. But if we compute the diametrical risk minimization in this case, and by the way, what does that mean? That means that we are solving this min-max problem that we had on the previous slide. We obtain a W. That W, let's plug it into the population problem and compare that with what we call the diametrical risk, which is the objective function in the problem we just solved. And in a way, this is kind of like the error that we have worried about. And it turns out in this particular example, this will be 0 if that gamma, which is the size of the ball that we allow V to live in, if that gamma is that same gamma that we have up here. So of course, by having such a gamma of that size, in a way, what the algorithm is seeing, it is seeing beyond that little dip. And look at the worst case in such a fashion, we'll realize that this dip is somewhat spurious and we'll avoid it in some sense, and we get a 0 error. Of course, this is a bit optimistic. Life will not be that simple, but you can see that there's potential. Here's my example number 2. This was the one that was a bit crazy, where the error for good old sample average approximation tended to infinity. It was an unbounded setting. Sample average problem would be unbounded. This is a situation where there's not Lipschitz continuity. How is diametrical risk minimization doing in this setting? Well, we can do a similar type of calculation. We're solving the diametrical problem. We're getting a W. And we plug in that W into the population expectation and see how we're doing. Well, in this case, the error is proportional to 1/root n. So I guess this is good news. Remember, it used to be infinity. Now is 1/root n. And what is a constant in front of that root n? Well, something involving gamma. But if you think about gamma as fixed, we see that actually this was a way of handling the situation. This was a horrible situation, for sample average approximation. By introducing this diametrical risk idea, we got control of the error. Okay, so this was a little bit, examples, but let's get a bit more serious about the analysis of this approach. And I'm going to do some analysis under the following assumptions. Imagine what you're trying to optimize over is these W's in a capital W set, which is compact. I'm going to assume IID is sampling, but I think there are many opportunities to extend beyond that. The loss function that we are minimizing the expectation or the sample average of is going to be rather general. For instance, it doesn't have to be Lipschitz, and this is one of the main points I'm trying to make. I'm going to assume it is Theodori. What does that mean? That means that it's measurable in the random side and then continuous in W side. So basically, the long and short of this is that I'm assuming continuity of the loss function. That's it, not Lipschitz continuity. In fact, it can be rather wild as long as you have continuity. There is a small integrability condition. It is not, we don't even need the expectation to be finite. but we need it to be bounded from above. So you can go down to negative infinity, but it's what we call sup-integrable. So there's an upper bound and is locally, so one can perturb locally the W and still have that bound. Okay, I think that's pretty mild compared to what other things that we have in the literature. And then there's an assumption about sub-Gaussian. And that is, of course, for some people, for statisticians, feel that maybe it's a little bit restrictive. I think there's also opportunities for people to go beyond that. The important thing for me here is that I don't need any uniformity in this sub-Gaussian property. So for any fixed W, this must be sub-Gaussian. But I don't need, for instance, the proxy variance to somewhat be uniformly bounded in some sense. It's a pointwise assumption, and I think that makes a bit of a difference. Okay, under all of that, what can we get? Well, here's a main result. So for some confidence level that I'm going to call alpha, that's going to show up on the right-hand side there. Then, so we high probability basically, and I made up a choice about gamma. Remember, gamma is the size of that ball that I'm using for perturbation. You see that there. Then we have the following finite sample size result. So with high probability, the difference between the population and the sample average in this diametrical setting, meaning that we're also doing a maximization, is bounded from above. Remember, I'm doing one-sided analysis. I'm bounding everything from above. Beta 1 over root n. Okay. So I'm getting the canonical rate here without assuming any Lipschitz continuity. I don't need to get into having a Lipschitz continuity and have the Lipschitz constant potentially causing results to get worse if the Lipschitz constant is big. But of course, what is that beta? We can look at that a little bit more carefully. Beta depends on gamma. Okay, it depends on alpha, size of W, and then the norm used. So maybe if you use the infinity norm, I think I have an example here. In the infinity norm or the sup norm, we see what beta depends on. I think the alpha part I'm not too worried about, not the size of gamma either. One thing I could be a little bit worried about is D. What is D? D is the dimension of W. Okay, so D is the dimension of W. So I'm really in the business where D over N goes to 0. So in a way, I don't fully address the modern applications or in machine learning. I really would like to have N larger than D. Of course, this result holds for any D and N, but that is where it would be more meaningful. Sigma, that is the proxy variance from the sub-Gaussian assumption. But of course, for which W you might ask? This is going to be the largest of them over a finite set that is can be characterized in some sense. Okay. One thing that you might be asking is, how big should that gamma be? How much should I be, robustifying in some sense? And that's, of course, an interesting question. And imagine, for instance, that you make the following choice, that gamma, the size of this ball is 1 over n, so 1 over the sample size. If you do that, what changes? Up now, I've assumed gamma has been fixed, but suppose we change it now to gamma depend on n. Well, the only ramification of that is that beta that you see up here now will involve a root log n term. So it will cause a bit of a deterioration, but only at a logarithmic factor. So maybe that is insignificant. So that shows that one can indeed having a smaller and smaller gamma, and still this in some sense have the same type of performance. Okay. I don't have too much time, so we could have talked a little bit about the proof. I'm trying to sketch that out. It does rely on typical entropy type of arguments. W is a complex set, so we can make a mesh out of it involving a finite number of boxes. The key thing in the proof there is that instead of what the classical analysis, for instance, you can find in Shapiro, Dencheva, Rosinski, where one will look at one point inside each of these boxes. Here one has to be a little bit more careful. The point to look at is selected carefully as where the population problem is maximized inside that box. And that is that point where one will make the argument about sample averages. And because this is picked at the maximum point, one can make some bounding arguments. And that is the key reason we can do this and get away with not having Lipschitz type properties that we, for instance, would find in Shapiro, Dencheva, and Rosinski's book. Okay. We could have talked more specifically. Maybe I should, based on Raghu Pasupati's talk earlier today about confidence regions, because we do have some confidence regions results here, but maybe in the benefit of time, I'll skip over that. But you see here, we can talk about confidence regions as well, under basically the same assumptions. I should probably have spent a little bit of time on how to solve this min-max problem. And I think that is a serious subject that we need to get into. If this does pass forward as a promising approach, of course, what we need to do is to find an efficient way of solving this min-max problem. We have somewhat of a heuristic here that mimics stochastic gradient descent. It mimics the typical way people do adversarial training, but I'm not going to get into the details of that. Instead, let me show you some numerical results. And I'm going to start with the MNIST dataset. Remember, the MNIST dataset is about recognizing handwritten numbers. So try to construct a classifier that can recognize handwritten numbers. And I'm going to make a comparison between what we are proposing, diametrical risk minimization, and what people call ERM, empirical risk minimization, which is just a good old sample average approximation. I'm going to do this on a data set that is a little bit spiced up in the sense that I'm going to introduce errors in the data set. So of course, I'm going to have a training data set. I'm going to work with that, but 50% of the labels are going to be incorrect or randomly selected to be incorrect. So maybe something that is a number 3 is going to be incorrectly be labeled as number 2, for instance, and that will of course add additional challenge in such a problem. Okay, so now let's go back to the original hypothesis that we had, which was that stochastic average approximation, or ERM, empirical risk minimization, if you like, has the tendency to fall into a valley that is rather sharp. And because it does that, it has a tendency, when you check it for the population problem, there's a tendency that obtained solution is not as good as you would have liked. And this is, of course, this downward bias that we're worried about. Let's look at the picture to the right and see if we can confirm that hypothesis. What I've done is that I have solved just a standard empirical risk minimization problem, optimized for so many iterations using stochastic gradient descent, this and that. And I obtained a training loss of, what is it? 0.2 or something like that. I don't know, something like 0.2. And then I generate 10,000 points in the neighborhood of that W and compute what is the training loss in that neighborhood. And I look at the value of those training losses. that produces 10,000 values. I'm making a histogram out of it, and that's what I produce here. So that shows me that I obtained a W that has a training loss of 0.2, but when I look around myself and look at other W's in my neighborhood, they have a much higher training loss, 2, 4, 6. So indeed, I have somehow dug myself into a deep valley where every W around me is rather poor. And this would be exactly the thing that I would like to avoid. Let's now compare this with the diametrical approach. I'm solving that min-max problem and I obtain a W that has a certain training loss. I don't know, maybe 1 or something. And then I'm looking around myself, 10,000 points, and look at their losses. And we see all those losses around me are 0.04, 0.05, 0.06. They are very similar. So I'm actually in a flat spot. Every W around me is roughly like myself. So indeed, a hypothesis that we had that this diametrical approach will land us in a wide open valley actually seems to be the case. But now let's look at the auto-sample performance. When we check this on the population problem, we get the same, a similar type of confirmation. If you look at the testing accuracy for the empirical risk, which is the red curve, it goes down as we train and we get into some sort of overfitting. We dig ourselves a hole, we get into a sharp valley. In contrast, if you do the diametrical, which is the blue curve, we are holding pretty tight with a good accuracy. That means that we have probably found a valley that is more open and we have a better, a much smaller error. Of course, we have done this in other examples as well. Here we have something about CFAR. Since I'm getting out of time, I just want to show very briefly that there's similar type of pictures there, similar type of conclusions. So it seems like also on CFAR, which is considered a bit harder problem than MNIST, we have the same type of behavior where the error is again much smaller for diametrical risk compared to classical empirical risk minimization. As late in the day, I'm not going to go into all of the details. I just want to show you that we do have this written up in a paper that is currently appearing in machine learning. And there's also a discussion about this and the underlying theory in our forthcoming book on optimization, which I'm preparing with Royset. Thank you very much for your attention.
Thank you very much, Johannes. It was a very interesting talk again. So, long day for some person, I think, but Tito is still there and raised his hand, so I will give him the word.
Yes, I don't want to hold people too long here. It's just 2 quick questions for Johannes. It was a very nice talk. One question I had, Johannes, is I was surprised we don't have to worry about the feasibility of W plus V in the formulation. So, because if this goes outside, but W goes outside the W set, anything could happen, but we shouldn't care about what happens outside W, right? This the set W. So shouldn't we have to impose that W plus V is feasible?
I think one could. You know, this was implemented in a learning setting where there were no constraints. But this was indeed, if you look back to the Rob Freund paper, where there was real constraints present, and then indeed they account for things like that you mentioned. Whether it is needed in all settings, I don't think so, but I think in some setting might be getting better result, because to some extent, if you're in a situation where you have a real constraint set, we can kind of keep that separate. We are just still in the business of trying to estimate expectation well, and we can think about, we're trying to estimate that expectation conservatively, and that's really all what we're worried about. And if we do it kind of overdoing it a little bit, that's what's happening if we don't limit V in that fashion that you say. So we will maybe make it a little bit extra conservative, unnecessarily conservative, and that could be avoided by introducing a constraint of that kind with probably maybe a little bit of complication computationally, but you will probably do better if you introduce a constraint, yes.
Yeah, it probably depends on the solution method, right? To do the min-max problem, whether that constraint is a... And the other question I had is, well, I noticed that all your examples early in the talk were highly non-convex. So do you think this approach is mostly useful in the case of non-convex psi functions, or do you think it regardless of that?
I think that is a good question. That was our primary motivation coming from statistical learning. The convex setting is, there's a little bit more regularity there, of course, and the Lipschitz requirement, and this goes back even to the questions of consistency and things like that. Often Lipschitz can be replaced by convexity, and you know that from some results. And but still, maybe convex is many different things. It could be convex that has rather steep changes and things like that. And maybe I think, although we haven't worked out the details, I think even in the convex case it could be beneficial to do this. Because if it's a very poorly conditioned convex problem, very sharp or something like that, then a high Lipschitz constant, then you might get better or reduced errors by doing it this way.
I see. Great. Thank you, Johannes.
Thank you, Tito. Thank you, Johannes. There was a question from Sven Leifer in the chat. Question remark regarding the regularizers that you use on page 2 on the slide 2. I don't know if Sven is still there.
Yeah, it's not very important though. I think it's clear. It was more a comment than a question.
Yeah, that was kind of neither here nor there. My example there was really just kind of motivational. I see, but I see you realize that now.
And there is another question in the chat that can be relevant too, from Chen and Sue. I can read the question, or I can give him the microphone if he wants.
Yeah, thanks a lot for the presentation. My question is that how often in SAA that are very sharp, as you're showing the example of fake optimal, happens, and we need to try to bring the solution to a flatter region?
How often is kind of a difficult thing to answer. I think we're talking about such a broad range of applications, but my understanding is that in many of these newer network architectures, they are indeed very worried about these kind of wide landscapes, and there've been a lot of paper with titles of the kind chaotic landscapes and things like that. So I think that is quite common in that domain. If you're in the more operational research type, classical stochastic programming, I think maybe the situation might be, say even a convex or mixed integer type plus convex type of setting, it might look a little bit better and the issue might be less. But we know already, even in rather seemingly well-posed problems, the downward bias of sample average approximation is real, is a big problem, and is been recognized for many decades. So I think just introducing a little bit of gamma, a little bit of less maximization can go a long way to help and reduce that downward bias.
Thank you very much.
Okay, and we'll give the microphone to Eugene Hahn. If you want to ask questions.
Oh, yes. Thank you very much for your very interesting talk. So my question is about the numerical experiments that you showed in the last part of the talk. So can you tell me more about how that min-max problem was solved and the comparison between the computation for solving that min-max problem and just the SAA problem without any diametric stuff?
Yeah, so,
okay. I may have missed
algorithm, and we'll talk about this in detail. Just I guess give you the bad news up front that basically running this takes about 5 to 10 times, or maybe more like 5 times slower than standard SGD. As you could imagine, that there will be some additional work. But as we have, if you're familiar with the progress that's been done in adversarial learning, we know that, adversarial learning also solving a very similar min-max, except the max part is now over the data space. There's been much advances in trying to do that min-max more efficiently. Various, there are papers with title like adversarial learning for free and these type of things. So I think there's much improvement that is possible in that, in that direction. And the algorithm that we're seeing here was really just a rudimentary implementation that we used. And I think the 5 times slower shouldn't be taken as a sort of fundamental limitation.
Okay, thank you very much.
Thank you, Johannes. Uday?
Excellent talk, Johannes. Thank you again. I think I should put my hand down, right? Hang on a second. Oh, sorry. Actually, my question was actually just moving ahead from what the previous person had asked regarding the computation. So the problem that you've been looking at is not the convex problem, right? So the saddle point problem that you're looking at is actually quite nasty, right? So I'm just curious if the scheme that you have, so it can convert. So what are the what is the limiting behavior of the sequence that you generate? Are you able to guarantee convergence to this some sort of saddle point, some local saddle point? What would it be?
Yeah, so this algorithm that I have on this slide, the heuristic, we haven't developed any result for it. I think for us, our primary motivation is see if we get a good empirical result, and we got that, and our goal was to get good statistical results without worrying about the numerical part. Although that is now an important question, and as I mentioned, if we are in the high dimension of the kind that we see in training on neural networks, I think one would apply any of the ideas that you see from adversarial training, adapt them, and I think that would be a reasonable, good approach, and there will be automatic results that will be available for that. If you're in a more low dimensional setting, where W lives in maybe thousands of dimensions, no more, then one can probably open up many other avenues. One can even attempt to, if there's other structure, maybe even to attempt to get that maximization done more accurately. Maybe it can even be done explicitly, not explicitly, but it can be carried out globally, that maximization. The many ideas one could imagine, but it is a min-max problem. you know, it is not going to be trivial to solve it. So I think that's an important area. But the question is, was it a good idea in the first place? And I think that is a good idea in the first place. And then now the question is, how can we do it better?
No, I think the results are remarkably promising in terms of the empirical behavior. So yeah, excellent talk. Thank you again.
Yes, thank you. I agree with you that it looks very promising. Just I will take the chance to ask one last question. In your numerical research, it seems that generalization error for your method is much more stable compared to traditional approach, because it's the if we take here, for instance, we see that the test accuracy remains high. In the same time, our set for the empirical minimization, people in machine learning, people often rely on cross-validation to decide when they start to observe overfitting and where to stop. So, as a good side, here it seems that your approach is less sensitive to overfitting. The bad side maybe, I don't know, is that how to decide when you stop. You said that you make a validation over 150 epochs. Do you have any idea how to decide that you are good enough to stop?
Yeah, that's a good question, and I think the way I approach this is the following. If I do plain vanilla empirical risk minimization, I will keep on minimizing, and I will be constantly worried about if I'm overdoing it. And as you mentioned, I will try to stop early or something, do cross-validation or something to make sure I'm not overdoing the optimization. If we do the diametrical approach, there's no danger of overdoing it because you're kind of building in robustness in some way. So you're going to just keep on hammering, because the further down you get the diametrical risk is really just the better. And so in a way, you should just keep going as far as you can to some extent. And you know, when you cannot get further down, the diametrical risk is kind of plateauing, then you probably will stop because of diminishing return. But there's really a smaller chance of overdoing the optimization, and maybe it's less critical to stop early, which is so important in other settings. But of course, there's a question of efficiency. That's another issue. But again, probably cross-validation will come in for the sake of, you know, can I get away with 50 epochs? Maybe, but that can probably only be settled through some sort of cross-validation process.
Okay, thanks a lot for the answer. And it was really a lot, again, this a lot of things to take back from at home from all these tools from today. It was a really great day. So I would like to close the days by really thanking all the speakers, the 5 speakers we had today. It was at least I enjoyed the day a lot.